we have discussed that computers may appear in different forms. They may appear in different places. They may be intended to do different type of tasks. But what makes a device to be a computer? What are the minimum components or modules that are required to build a computer? Here we are not going to look at any special type of a computer. We are not looking at either desktop computers, notebook computers, or even embedded computers that are inside other devices. So let's look at the logical organization of computer and to see how different components are interconnected. We all know that computers are meant for processing data. That means the computer should have some module or some mechanism to get data into the computer. And for that, we use input devices. The most common form of input devices will be the keyboard and the mouse that you see in your conventional computers. But some other forms of computers may have different input devices. For example, a computer inside a refrigerator or a computer inside an air conditioning machine may have a temperature sensor that measures the outside temperature and then provide that as an input to the computer. Another device which requires a measurement of physical force may have a force sensor which can measure the force applied on a certain mechanical component and provide that as a digital data to the computer. So likewise, different devices may have different type of sensors that can work as input devices. When the data is processed inside the computer, we are going to have outcomes or results. These results has to be sent to the outside world. For that, the computers has output devices. The most common form of output device, again, will be the screen that you see on your normal desktop or notebook computer and the printer that you connect to the computer to take a hard copy of the output. But like the input devices, there can be other forms of output devices. Some computers might produce a signal which can be used to turn on or off an indicator light. There can be audio produced as an output. There can be devices which can convert output from the computer into a mechanical force like a motor or some kind of an actuator that can exert some mechanical force on a particular mechanical component. So likewise, there can be different type of output devices. Apart from these two, computers has to deal with lot of data, which means inside the computer, we need to have a mechanism of maintaining data. For that, computers use memory. There are two types of memories. There's volatile memory that can keep data as far as we have power applied to the computer and the computer is working. There is also non-volatile memory that can keep data over a very longer period of time, even when the computer is switched off and no longer operational. Now we have a mechanism of getting data into the computer, getting the results out of the computer, as well as keeping data inside the computer. Where do they get processed? Now for that purpose, we have another component, what we call the central processing unit. As the name implies, the central processing unit is central for all data processing activities that happens inside the computer. Every bit of data that get changed happen inside the CPU. Data resides on the memory, but they go into the CPU to get processed. And when they are processed, they are sent out of the CPU again, either to the memory to store as results or to output device, give them back to the real world. Now we have these four devices. How they interchange data between them? For that, we have another component called the system bus. System bus interconnect all the devices in the computer with the CPU. It connects memory to the CPU, it connects input device to the CPU, it connects output devices to the CPU. It's a common set of communication lines or a communication channel that these devices can use to share data between them. Now, when there are many devices connected to the same communication channel, we should also have a mechanism of identifying each device in this channel. Like on a road, beside the road, we have a lot of houses. We identify each house along a road using its address. So likewise, all of the devices, each and every device on a computer also has an address. Now, when the CPU wants to talk to one of these devices, either to send data or get data from them, CPU uses this address. Through that address, the CPU can identify each device uniquely which is connected to the system bus. So these 5 components make the basic computer. Depending on the nature of the computer, depending on the purpose for which you are going to use the computer, depending on its size, capacity, etc., the size and the nature of these devices can also change. But we need these 5 devices to build a computer. So in terms of the logical organization of computer, these are the critical 5 devices that are required. In conventional computer systems, 3 of these 5 components, that is the CPU, the memory, and the system bus, is often packaged into one single unit, which is technically referred to as the system unit. In a desktop computer system, what we get as this one large box containing everything, it is that system unit. Often we refer to the system units as the CPU, but that notation is wrong. CPU is only a single part or single module inside the system unit. It also includes several other components, memory, the system bus, as well as several other components that helps the CPU to function correctly. In small computer systems, for example, in an embedded system that is included inside some other device, the CPU, memory, and system bus are so small, so miniaturized that they can be packaged into one single integrated circuit or one single chip. The PIC microcontroller, the Atmel microcontroller, or the Arduino board that you see, some of you may have seen already, are such examples. In these cases, the input devices and the output devices are connected directly to this integrated circuit, which include the CPU, memory, and storage as one single component. It is no need to say that a computer is a very complex piece of equipment. It's versatile as well as it's very complex. Therefore, sometimes it is difficult to think the entire computer system from a one single way. There are too much of details that we need to consider. To support this, when you look at computer from an engineering perspective, we often define 2 different models of the computer or two different views of the computer. In one view, we look at how its hardware is organized. We look at things that a typical hardware engineer might want to know about when he wants to build a computer. That model view is called the hardware model of a computer in terms of its logical organization. Then hardware itself can't do anything. The versatility and the flexible nature of the computer comes from the software that runs inside the computer. So without software, hardware can't do anything. So we also need details about how software can be written in the computer. That point of view is called the programming model of a computer. In a programming model, we look at how instructions can be written, how sequences of instructions can be written to do some useful tasks using the capabilities that are supported in the computer. On the right hand side of the screen, I have shown you a part of a program that is written to a particular computer system. And you will notice that even though it looks like a program that someone has written, the statements and the commands that are found in the software are not the Python commands that you are familiar with. It's not the Python language that you have done in your laboratory classes. This is because this program is written in a different programming language. It's written in a programming language called assembly language or sometimes as machine language. The difference between Python and assembly language is that assembly language has operations or commands or statements that are much closer to what a CPU can do. So they resembles what CPU can do. We will be learning more about assembly language programming and machine language instructions later in this course. But before that, let's look at some of the features in this hardware model and programming model. What are we really concerned in these 2 different views of the computer? The hardware model is there for the people who build computers. people who will get different components from various sources and combine them or integrate them to build the circuitry that makes a computer. So they are concerned about certain aspects when they do the task. For example, they would want to know how much or how many input devices or how many output devices that they need to connect to the computer, because for each connection they need to provide some provisions. Then they will also know what addresses to be assigned to these devices, because for the CPU to communicate with those devices through the address, to the system bus, they need an address. Then they will also be concerned about what type of memory to be used, how much of volatile memory to be employed there. And there are different types of volatile memories that have different features. So what type of memory to be used, how much of non-volatile memory is needed. And again, for non-volatile memory also, there are different types of memories that can be used. So which type to use. Then how activities of different components of the system can be synchronized. For example, when the CPU sends some information to the memory should be ready to get that and store it in the memory. Similarly, when the CPU asks for some information from the memory, some data from the memory should be in a state ready to send that data to the CPU from memory. And also, same thing applies with input-output devices. The CPU should know when the input device has something to be sent to the CPU. It should know when an output device is whether an output device is ready to accept data from the CPU. Apart from these functional modules that we are familiar with, there are other concerns also. For example, how much power this computer will need to operate. So because you need to provide a very accurate power supply to the circuit. So how much capacity that power supply would need. Not only that, every component consumes this power and convert that power into usually heat, because energy cannot be destroyed. The energy has to confirm. The electrical energy that you provide to the computer has to be converted to some form. There's no mechanical energy in a computer. So all the energy that goes in will be converted to heat mostly. So then how much of heat these components will produce, and how do you remove that heat without allowing the computer to overheat and get damaged. So how much of fans you need to put, or any other cooling system that you need to put. So all those kind of hardware oriented parameters which need to do this hardware circuit design will be of concern of the hardware model. On the other hand, if you are writing software for the computer, you may not be concerned about most of these things. You may not be concerned about how much power the computer is going to consume, how much heat it is going to dissipate. I mean, they are not the concerns of a programmer. But on the other hand, there are certain things that the programmer will need to be concerned about. For example, how much memory is available in the computer and how the memory is organized. Whether I can store in terms of bytes, whether I can store in terms of Unicode characters, whether I can store in terms of a larger word, etc. Then the programmer need to know what are the addresses of each devices, because if you want to send that data to a particular device, he should know what is the address of that device. Then what type of data processing operations are supported in the CPU. For example, whether the CPU can do addition, whether it can do subtraction, whether it can do multiplication and division. If multiplication is not supported, you may have to do multiplication by repeated addition. So the programmer need to know whether that particular operation is supported. Now, when you write in Python language, you are not concerned about these things. But when you write software in assembly language or machine language, these are concerns because they are linked to the capacity and the capability of the processor. Some processors do not support fractional numbers. They support only integer numbers. Then you need to simulate fractional numbers using integer numbers through your software. Then you will also be concerned about how does CPU know whether an input device or an output device needs its attention. For example, when an input device is ready to send some data, it needs CPU attention so that it can send that data to the CPU. When an output device is in need of data, or when the CPU wants to send data to the output device, there should be a mechanism whether the CPU can check whether the device is ready to accept data. So likewise, there are different concerns that the programmers or the people who write software need to be concerned about about computers. Now you will also notice that some of these operations are very closely linked to each other. For example, the programmer might want to know what are the operations that the CPU is supporting. And that comes from the hardware design. A particular CPU will support certain type of operation and it will not support some other types of operation. How much of memory is available? That's a concern for hardware also, because when you design the memory, you will allocate certain amount of memory for different purposes. And what are the addresses assigned to the input-output devices? So that's a concern for the hardware, because they need to design the circuit to assign that address, and the software programmers or the programmers who write software to the computer need to know those addresses so that they can communicate with the other devices. So even though we look at this hardware model and software model separately, sometimes we see there's an overlap between these two. And in this course, that is the place where we will be mostly concerned about. In a while, we will look at how CPU actually do this data processing task.